This is going to be a relatively short presentation. I'm just going to kind of wrap up the UML discussions that we've been having. So we discussed two methods for doing systems analysis and design. There's two kind of broad methods. You have this traditional approach where we talked about using the software development lifecycle in conjunction with the Gain and Saracen data flow diagramming along with ER, entity relationship diagramming. So that was that's one technique. And then there's this more modern technique with UML. So UML, or the Unified Modeling Language, is a standard, right? So it's a standardized modeling language, unlike Gain and Saracen, which is not standardized, although it's implemented much the same way across many organizations that use it. But what we're finding is more and more organizations are using UML to represent designs for information systems and for software systems. So going back in time, just as a quick narrative here, if we go back to our Gain and Saracen data flow diagramming and our ER diagrams, really we only had two models that we talked about for modeling systems using that traditional approach. But then with UML, we have many more models. Now, so far, with UML, we've only talked about the use case model and the class diagram, which shows objects or things that our system has to remember. So in this unit, I'm going to expand on that a little bit and show you some of the other models that are available to us in UML. And one thing I want to talk about real quick is that with the Gain and Saracen data flow diagrams that we talked about and the ER diagrams, there really isn't much relation between those diagrams, right? They're not related to each other. Other than the sense that maybe they're describing things in the same system that we might design, but they're not directly related to one another. Now, now within the data flow diagram, we had our context level diagram and our level 1, level 2, and so forth and so on, and those were all interrelated, but there's no relation between that and our diagram for entity relationships. Where our UML is much different is that UML is not just a bunch of different diagrams or a bunch of different models that stand alone, but rather those models are fully integrated. So these are all models that integrate with each other to basically get a better understanding of the design for a system. And that's really the power of UML. So UML is not just a bunch of diagrams that we learn and we can use them independently, but rather they are related to each other and they stand together to describe a system. So far with UML, I haven't really talked about much. I just only talked about these two diagrams. We talked about use case diagramming, which by the way was very similar to context level in the data flow diagram. And then I also talked about the class diagram, right, which shows our objects and our things. Now when I talked about use case diagrams, I also talked about how we can make a fully developed use case description, which is much more detailed. I'll review that here in just a few minutes. Then I also talked about activity diagrams when we went over use case for UML. Now, if you remember, the use case diagram is all about what our system should do, right? What are the functional requirements of our system? What do we expect to get out of our system? That's the question that is answered by the use case diagram. And then when we make our activity diagrams, which are, we embed those in our use case descriptions to fully, to help explain those use cases that are complicated. The activity diagrams are all about what the system does, right? And then our domain class diagram are the things that our system has, right? The objects or the classes that our system deals with. One of the diagrams I'm going to teach you about in this presentation is the state machine diagram, which shows us how things can change, right? So how things can, through the life cycle of a thing, what are the phases it goes through, right? For example, humans, we start out as babies, then infants, toddlers, tweens, teenagers, young adults, and then geriatric, right? So we go through these sort of states of being as a person. And likewise, we could take all of our classes and we could diagram or model how those things change throughout their life cycle within the system. And that's what the state machine is going to tell us. But again, our concentration there is not so much about the activities of the system or the behaviors of our system, but rather the things in our system and fully defining those things. But a state machine diagram relies on the class diagram. When you create that state machine, it sort of relies on what you created in the class diagram. And likewise, your activity diagrams are interrelated with that use case diagram. And our use case descriptions obviously are related to our use case diagram. Everything, it kind of decomposes that use case, right? So the activity diagrams and the use case description decomposes that use case, just like our state machine is going to clarify and further define our classes from our class diagram. Now, so far, these look like they're disconnected, right? They're on two different sides of the slide. But we're going to learn about another model in UML called sequence diagrams. And a sequence diagram more or less sits in the middle here. It's a combination of the use cases along with the class diagram. Now, if you remember, when we created our class diagram, you had three areas in each class, right? You would define a class. The top was the name of the class and its stereotype, like persistent or border, boundary class or something like that, or a database class. And then your state machine diagram, could further clarify, the different states that, which I'm going to show you today. But if you recall, the very bottom of that class diagram had behaviors or methods, right? So a use case is all the functionality we expect to get out of our system. An activity diagram shows sort of the steps to complete some of those use cases. Then a class diagram shows the things that we use in that process. So a sequence diagram is the combination of all of those things. It's basically, in your sequence diagram, you're going to show the sequence of events and the steps to complete a use case, which objects are being used or classes are used in those steps. And if you're going to, those arrows that are going to go back and forth between different classes in our sequence diagram are going to represent basically methods or behaviors, which were in the bottom box of a class diagram. And anything that's being transmitted back and forth between classes to complete a use case must also exist as an attribute or a property in the class diagram. So we can model our entire system. Basically, that sequence diagram sits in the middle. To me, I believe that the sequence diagram is one of the most important diagrams in our in UML modeling, because it sort of shows us how everything works. It's a very, when as somebody who's writes code, I think you would find that sequence diagrams are very descriptive of a system. And as you get questions, you can go back and look at those other diagrams to kind of decompose in your head, how is this really supposed to work? So I just wanted to talk about that in the relationships. Now, we've talked about some of this before, right? We've already talked about use cases and the use case diagram. And then I talked about how we have use case descriptions, and you can use activity diagrams. And then I'm going to talk about sequence diagrams today. And of course, we talk about class diagrams, which have our state machines, which I'm going to talk about in this slide deck as well. So for our use case descriptions, in the beginning, you write a very brief description for each use case, but we can more fully define those use cases with a fully developed use case description, which, again, we talked about this earlier. So you would typically have all of these different sections, which we talked about. I think I showed you kind of a similar list of things that you might have in a fully developed use case description, and here's what it might look like, right? So this is an example of what a fully developed use case description might look like. This is just a larger version, if in case I'm showing this in a classroom, but in the overhead. But so use case descriptions, again, it's going to have the use case name, the scenario, the triggering event, a brief description, who the actors are, and then we're going to get into any related use cases. So that would be anything that uses the include stereotype within the use case diagram, who the stakeholders are, preconditions, in other words, what has to be true before the use case, what's going to be true after the use case, which might be useful for testing, which we'll get into later. The flow of activities, which we could explain with an activity diagram, for example, and then what we're going to do when things go wrong, right? And then our activity diagram would look like this. You would have your initial state, and then you have your actions. You can have decisions. Different things could happen. You can split execution paths, and then you can rejoin execution paths, and then finally have a final state, which shows you, when this process is completed. So it's an example of an activity diagram. And I think I probably gave you an example of showing maybe a dialogue between the customer and the system and what that might look like as a series of activities. Of course, this one's very simple. There's no decision splits or merges or joins or anything like that. So now that we have that solid understanding of the left side of our UML diagrams, which is all of our behavioral models, what does the system do? Let's switch gears and go back to the right side of my diagram before and look at the structural models, one of those being the state machine diagram. And a state machine diagram is basically a UML diagram that shows the life cycle of an object and its states in transition. So a state is basically a condition during that object's life. When it has some kind of criteria, or it's performing some action, or it's waiting for some kind of an event, right? It has some kind of condition that we want to show in a state machine. In order to get to a state, you have to transition to a state. So it's the movement of an object from one state to another, right? So we have to still go from one state to a different state. The action expression is the description of activities that happen to transition that state. So you have to do something in most cases in order to get from one state to another. The pseudostate is a starting point in the state machine, which is typically a black dot. And the origin state is the object before its transition. And the destination state is the state after a transition. So a guard condition, which I'm going to show you in a second, is basically a true-false that tests whether a transition can actually fire, right? So that we're checking to see if we can modify the state, or if the state can transition. So a guard condition defines whether or not a state is able to transition from one state to another. And I'll show you an example. So imagine you have a printer, right? I've got a printer sitting on my desk, so I'm going to use that as an example. And I think most of us have printers. And when you think about it, a printer, from a very high level, the printer has two states. My printer can either be off or it can be on. If I'm in the on state, to transition my printer to off, I hit the off button. So that's my action, right? So I show on that state, on that transition arrow, right? The arrow that's going from on to off is my transition. And its action is off button pushed. So when you push the off button, it transitions from on to off. I could also have a transition from off to on, right? So if I hit the on button, it's going to transition from off to on. Now, there's two other things happening there in that description. And by the way, just some of the syntax here. So there's our beginning pseudo state, which is the start of the state machine diagram, and then and then you have your actual states in those boxes, which you can see here. And then a transition is what moves something from an origin to a destination state. Now, in my example on the top, going from off to on, it's a little more complicated. We have our transition, which is on button push, right? So that means somebody hit the on button on my printer. There's a guard condition that checks to make sure the cover is closed, right? If you're changing the ink and you have the printer open, it's not going to let you turn it on, right? While you're trying to change the ink, you have to turn it, you have to close the cover and complete putting the ink in there before it'll let you start it up. So my cover has to be closed before it allows itself to transition from off to on. And when it's turning on, it does a self-test. Now, the self-test is something it does during that transition, but it doesn't have to pass that self-test to turn on, right? For example, if it does the self-test and realizes there's no ink, it still turns on. It just tells me there's no ink, right? But it's still in that on state. So that's an action expression. So three parts to that transition: a transition name, the guard condition of what has to what has to happen before we can transition, and then an action expression is something we do while we're transitioning from one state to another. Now, as I said, that when I'm hitting that on button, we do a self test. There's other things that there's other states we could possibly have. So I could decompose that on state to even more states, right? So my printer is idle when it's turned on, but it can go from being idle to when I send a document to it, then it's working. It's printing a document, right? So if I print a document, it transitions from idle to working. When it's finished, it goes back to idle, right? So the guard condition is it done printing something? Yes. Then it transitions back to that idle state. As another example, right? So within this on state, I can have other states, right, that can concurrently happen. So when it's idle, it could also be empty. And if I fill the ink cartridge, then it's full. And when the ink is getting low, it generates the low message, and then it's in the low state. And if I fill it up, it goes back to full. But if I don't fill it up, eventually it's going to transition itself back to empty. So that's a simple example of some additional states that we might have. So I kept kind of decomposing that a little bit, and it's possible for an object to have many states at the same time, right? So my printer can be both idle, empty, and on all at the same time. Okay? All right, so these are the steps that you would take to create a state machine. So you're going to look at your class diagram that you created earlier, and you're going to select classes that might require a state machine diagram. Not everything requires a state machine diagram. You would do this with objects that are particularly complicated. So if you're taking one of my courses, you're probably doing a project that I like to use. I have a project where we develop a design for a system for a package delivery company, right? For a company that basically is a courier company. And of all the states that you might, of all the objects or classes that you might have on your class diagram, I can almost guarantee that everyone that designs that system is probably going to have a class called package, right? And packages probably are going to be really important for having a state. That's something I probably would want to decompose and show all the different states that might exist for that object. For example, a package could be waiting for pickup, it could be on the delivery truck, it could be in the warehouse, it could be getting processed, it could be being delivered, it could be delivered, right? It could go through all of these different states. So it'd be important for me to show all of those states because I think that would really help the programmer who's developing a system or anyone who's trying to understand the system. It's really going to help them understand how that works, how a package works. And it's really core to the system. A customer, on the other hand, there's probably not really anything to gain by doing a state diagram about a customer. Or maybe there is, I don't know. But a payment, maybe that does have something, maybe there is something to gain about diagramming a payment, for example, a payment object. Maybe the payment's pending, maybe it's been approved, or it's late, or something like that. So basically, these are the steps that you're going to use. I don't want to go through all the steps, but these are the steps that you're going to use to create a state machine diagram, similar to the one that I created before. So I have a simple example here. This is I've used this in some of the other slideshows. This is from one of the textbooks that I use. This is from a Cengage textbook called, I think it's called Analysis and Design in a Changing World. So it's Object-Oriented Systems Analysis and Design in a Changing World. And it has a project, basically a running project throughout the text that talks about a system for, it's a system for basically a customer loyalty program, right? It's a customer loyalty program. It's a fake store that has a fake customer loyalty program. But one of the things that I try to diagram in that textbook that we always look at in classes is maybe making a system for that store for selling things online. So this might be a state machine for an order, right? So an order could be added. It could be on back order, it's ready to ship, or it's shipped, right? So you can see some various states there. And we can decompose that even further. Oops, sorry, I have the slide here twice. But we can decompose that a little bit further. So when it's on back order, in order for it to be ready to ship, the item must have arrived. If we can also mark it as back order to go back to the back order state. Once it's ready to ship, we ship the item, and then it goes to the shipped state, and then it gets archived, and it has an end state. That's a pseudo state at the end, by the way. It looks just like the one from the activity diagram. We can even get a little bit more involved here. We can keep decomposing this a little bit to get more involved. But as you can see, this really starts to clarify exactly what a order, what these different states are for an order. In fact, if you look here, once the order is in shipping, then it has some various states within shipping, right? So if it's in the shipping state, it could be being shipped, or it might be waiting for back orders. Then it transitions to shipped. So this is probably a good example of what the state machine might look like after we're done revising it and after we're done sort of, making a final version of that diagram. Now switching gears a little bit, so this is the last diagram I'm going to show you for UML. There are lots of other UML diagrams that you could learn, and in this course I didn't want to show you all of them. I'm showing you sort of the important ones, the really good ones that you would need to know, and at a minimum, the 3 diagrams that I think are important in UML for system design are going to be your use case diagram, because that starts everything, and then your class diagram, and then your sequence diagram, which is sort of a combination of both of those. Our sequence diagram is informed by those other 2 diagrams, and they're sort of interrelated. But we need all 3 of those to really get a good idea of how a system works, right? We have to look at all 3 of those, and we have to reference all 3 of those. So a UML sequence diagram is basically it's a diagram that shows you how the system works over a time period, right? In fact, we call these lines that you see on here timelines. So you have your actors or your classes along the top. So if you want to show how an actor interacts with the system, you certainly could show it on a sequence diagram. When you do that, they call it a system sequence diagram. Or there's a design sequence diagram which shows all of the classes and how they interact. And I'm showing you here just a system sequence diagram. So you have your object, which is underlined in a box. Then you have your lifeline, which, so what happens is the movement of time is from the top down, right? So if I start from the top and start looking down my timelines, I see where does the first line start. So this process starts with inquire on item, right? And it goes and asks the system about an item, and then the system responds with a message with the item information, for example. So you have input messages and return values, and I'll show you some different ways to show that on a diagram. And then you can have optional notes that explain something in the diagram, and this is just the symbol that you would use from UML. I've seen people use different symbols for that, so it's not terribly important exactly what the shape of that symbol, but if you wanted to follow UML, then for sure it would look like this. So let's look at some examples here, but before I do that, I'll talk about some of the syntax. So an asterisk indicates repeating or looping messages. Brackets are true-false conditions, just like in our state machine diagram. The message name is a description of the requested service, and it is omitted on dashed line return messages, which only show the return data parameters. A parameter list with parentheses on initiating messages shows you the parameters that are being passed from one class to another. And a return value is what that class is expected to return to whoever initiated that message. So as an example, if we wanted to show looping, for example, this is what a loop might look like. So you have your test condition for repeatability. So for example, if this is my system for putting things in a shopping cart, we're going to loop for each item in a shopping cart. So for each item we have in that shopping cart, we add the item. The parameters that we have to send to the system in this case are going to be the item ID and quantity. And then it's going to send back the description and price. That's the expected return, and that's what the dotted line shows is the return. This is one syntax for doing this. You can also show it this way at the top. This shows exactly the same thing, where we loop through adding items, right? So we loop through the add item that you see here, and then for each item that we add, if there's another item, we keep going, right? That's the guard condition. Is there another item? We're going to pass the item ID and the quantity, and we expect to get back a description and a price. So what you see after the equal sign is what we're sending to the other system, and what you see in front of the equal sign is what we expect to get back from the other system, along with the guard condition. So that's a simple example of a loop. You can also do conditions, right? So an opt frame is basically what you might call an if or a conditional in a programming language. Oops, let me go back. Sorry, I didn't mean to go forward there. So for example, our guard condition here is if they selected an accessory, right? So that's our condition. Did they select an accessory? And if they did, we're going to add the accessory, and then we get back the accessory details from the system. Likewise, you could do alt. So alt is basically a sort of like an else if, right? So here, if it's a taxable item, we're going to add the sales tax location and get back the amount of the sales tax. Otherwise, we send an exemption code, or we ask the user for an exemption code, and then we send back their tax exempt detail. So this would be a conditional with an else. So our steps for creating the SSD or for a sequence diagram is you identify an input message, describe the message from the external actor, and then you identify any special conditions, identify and add return values, and then finally get your system sequence diagram. It's a relatively simple to think about. I'm going to rephrase this a little bit though, because in this presentation I don't have design sequence diagrams, which I think are also important to understand. A design sequence diagram, what we're going to do to create those is look at our use case diagram, and for each use case in our use case diagram, we are going to look for all of the classes that are going to be involved in the completion of that use case. So the first step is identify a use case, and then show all the classes along the top of your sequence diagram that you would need to complete that use case. Then you're going to draw your messages going between all the different classes over time, representing all the steps to complete that use case that would show all the messages. Now here's the thing, as you're drawing these lines from one class to another, if you have a line going from one class to another, the only way a class can ask another class to do something is if a behavior or a method exists to do that. So if I'm asking a class to get me the sales tax amount, then that class needs to have a method to support that. And if I'm going to get back some property, that class I have to have that property in my class when I get that message back in order to store that result that comes back to me. So, and by the way, if I'm going to give information to another class, they have to have that property, right? They have to understand that property on their side. So you get a sense here of how these diagrams are interrelated, because I can't tell a class to do something if it doesn't have the capability to do it, right? Or if I don't have visibility to do that, right? This is where the visibility comes in that we talked about with our class diagrams. So these are powerful diagrams in that they are all interrelated. And what I'd like to do is I'll probably post another video that shows you some design sequence diagrams so you can see what those look like. But I just wanted to show you some examples of a diagram here. So here's an example of a sequence diagram that includes a loop. Now this diagram only shows the actor in the system, and we call this a system sequence diagram, meaning it's only showing how the actor interacts with the system as a whole. But to do a design sequence diagram, we would decompose the system, and we would have all of the classes in the system that are required to complete that use case. And they would show how all of those different classes are talking to each other. By the way, there's also a sequence diagram that I use. I don't know if UML really defines this, but I call it an integration sequence diagram. And this is where I show different components of information systems, or really different information systems altogether, and how they integrate with each other to complete a use case. For example, I work in healthcare, so if a patient is registering or if a patient is checking in for an exam, we might have many different systems that work together to complete that. So there's a billing system, and then there's a system for verifying insurance that's completely external usually to a healthcare provider. And I'll show the different APIs and how these APIs work together over time. So I think what I'll do is record another video for you showing that and how that works. But that's a system sequence diagram. So again, we talked about our use cases and our class diagrams earlier in the course. I started out with our use case and our use case descriptions and how you can decompose that with activity diagrams. Today in this slide deck, I tell you a little bit about state machine diagrams. And then finally, I showed you how all of this stuff works together to give us a sequence diagram, which is a very important diagram for showing, for giving us clarity on how a system works. And that's it. So that's extending our use case models. And if you have any questions, let me know.